In the year 2000, as the world celebrated the turn of the century, a widespread assumption took hold that humanity had reached a developmental peak. The general consensus was that technology had finally reached its ultimate form, yet our infrastructure remained remarkably inefficient. We relied on sluggish electric vehicles, managed data through labor-intensive manual systems, and traveled to space by burning millions of pounds of solid fuel in rockets designed to be discarded after a single launch. The true limitation of that era was a stubborn acceptance of these physical constraints. We operated within a status quo defined by high-friction, single-use machines because we assumed those limits were permanent. The technological shift of the next 2 decades focused on a deeper objective, rewriting the internal logic of machines to mimic the adaptability of our own biology. In the early 2000s, the global automobile industry operated with a mathematical certainty. Building a reliable car for just 1 lakh rupee was a physical impossibility. In 2008, Ratan Tata challenged that conclusion. Tata Motors engineered a completely new 624cc 2-cylinder engine specifically designed to meet that exact price point. As this diagram shows, the mechanical breakthrough involved relocating the engine to the rear, which removed the need for a long, heavy driveshaft. This single structural change earned 34 patents, drastically reduced production costs, and expanded the interior cabin space. Moving from the ground to orbit, aerospace engineering faced an even more extreme constraint. Space agencies routinely spent hundreds of millions of dollars on hardware that was destroyed within minutes of its first use. Then, in 2015, SpaceX successfully reversed the trajectory of a rocket booster mid-flight, guiding it back to an ocean drone ship and touching down perfectly upright. By proving that the most expensive part of a launch could be recovered and flown again, SpaceX removed the financial requirement of building a brand new rocket for every mission. By stripping away unnecessary driveshafts and ending the era of disposable boosters, these inventors proved that hardware could be re-engineered for levels of efficiency that were previously considered mathematically impossible. Heading into the 2010s, electric cars carried a heavy stigma. They were widely dismissed as slow, compromised vehicles with inadequate battery range. The 2012 Tesla Model S changed that perception. Built around a massive vertical touchscreen, the vehicle functioned as a high-performance computer that happened to have wheels. Because the car's core functions were software-defined, Tesla introduced over-the-air updates. This allowed navigation, climate control, and battery efficiency to improve while the car sat in a garage without ever visiting a mechanic. That same software-led logic fueled the explosion of artificial intelligence. Tools like ChatGPT demonstrated that software could parse and organize massive datasets in seconds, tasks that previously required weeks of human labor. This shift toward automated data processing solves the primary friction point for growing companies: manual data entry. This transition to software-led systems allows machines to self-optimize and handle complex data, removing the mechanical and human friction that defined the previous century. By the mid-2010s, one final barrier remained: the physical gap between technology and the human nervous system. In 2015, Elon Musk launched Neuralink to bridge that gap, focusing on the development of computer chips designed for direct implantation into the human brain. This diagram shows a brain-computer interface. It intercepts neural pulses, translating them into wireless commands for an external computer. In recent trials, this link allowed paralyzed patients to move cursors and play video games using thought alone, bypassing the need for physical movement. This direct link removes the physical body as the necessary middleman for technology, allowing a thought to generate a digital command with the same speed as a neural pulse. In 20 years, we have progressed from re-engineering the internal combustion engine to recovering falling rockets and translating human thought into digital action. This progress suggests that many of our perceived boundaries were actually thresholds of efficiency. When we re-engineered the mechanics of the engine and the orbital trajectory, the impossible became a standard procedure. Humanity does not passively wait for the future to arrive. We are the architects who build it.